What's up everybody, I'm David Wilson and welcome to the Dev Aspect. In this episode, we're going to start developing a command parser for our simple text-based adventure game using parser combinators. A combinator is a function that takes two other functions and combines them together to achieve more complex behavior. When parsing text, a parser combinator is a function that takes two parser functions and puts them together to make a higher level parser. What this achieves is the creation of a recursive descent parser, because you're basically building layers of parsers up from the very core elements to the higher level language constructs based on the grammar of your language or whatever it is that you're trying to parse, which in our case is text-based commands. Now, since our game has a really simple text command format, we could just split the string based on spaces and then just parse the command really simply, just using what pieces of words we find inside of the command. But for this episode, I thought it would be interesting to try to develop our own set of parser combinators so that you can see how functional programming can be applied to something like text parsing. Parser combinator libraries are actually quite common, and there's a really good one for F# called fparsec. So if you like what you see in this episode and you want to learn more about how to use parser combinators, you should definitely check out the fparsec library so that you can see what kind of combinators that they provide, and also how you can design really complex parsers using these kind of combinators. So since the coding section is pretty jam-packed today, we're just going to jump right into the code and learn how to write parser combinators using F#. So before we get started, I wanted to point out something that's going to be a little bit different than the previous episode. And that is that I've changed the font that I'm using for the code to a font called Recursive. This font is really interesting because it provides some special characters for programming languages, and they are exposed as ligatures in the font so that common symbols actually show up in a nicer way. And to give you an example of this, let me see if I can find a pipeline. So if you see, there's this triangle here, which is basically the pipeline character. And if I separate those two characters, you'll see that it's really just a pipe and an angle bracket. But once I put them next to each other, it turns into this triangle. Same thing for the bind operators here. They actually have a special ligature for bind operators. So I've been enjoying using this font so far, so I decided to give it a shot for this episode to see if it helps make the code more easy to read. If you want to download this font, you can go to the link below in the description. And once you do that in Visual Studio Code, you'll want to open the File, Preferences, and User Settings page. And then you can see that I've set the font family to Recursive. And then I've enabled the font ligatures option so that the editor will detect these ligature characters and then show the real symbol whenever they're put together. So let me know in the comments if you think that this font has actually improved the way the code looks in the episode. And if it has made the code a bit more difficult to follow, let me know, and then I'll switch back to using the previous font from before. All right, let's get started. So as I mentioned before, today we're going to write some code that parses the simple text commands that the user will type to interact with the game world. So the type of commands that we're going to try to parse are really simple. So they're going to be just, multiple words like a sentence separated with spaces. So if you can imagine something like go west, or take key, or potentially even something like take key from bag. The grammar for these commands is based on having a word at the very beginning that is understood to be a command, and then some words following that are usually parameters to the command, and maybe other static words like from, which helps set the context for later parameters. So today we'll write the code that sets up the initial parsing structure for this type of command. And in true functional style, we're going to try to build this parser from the ground up using simple functions that are composed together to make more robust parsing behavior. So our model for the parsing functions will be based on commands that take a list of characters and then return a result that contains the parsed result and the list of remaining characters. This result also can return an error to say that the command doesn't actually conform to the expectations of the parser. So let's start writing our parsing functions with the most basic function possible, which is the expectChar function, which takes the list of input characters and then looks for a specific character at the very beginning of that list, and then returns that character if it actually is found. So the first parameter will be the expected character, And the second parameter will be the list of input characters. Since we know that our input is a list of characters, let's go ahead and use a match expression to break that list down. And the nice thing about lists in F# is that they have some really nice syntax that you can use to decompose the list. The most common thing that you want to do when decomposing a list is taking the first item from the list and also getting the remaining items from the list. So we can do this with the : symbol. So we'll say C : remaining chars. And this will decompose input chars to give us the first item as C and the remaining items in the list as remaining chars. So now we need to see if the character that's at the front of the list is the one that we expect. So we'll use the if statement and say if C equals expectChar, then success, and for our success value we're going to return a tuple that has the parsed value and the remaining set of characters. And in the case where we receive a character that we weren't expecting, we need to return some kind of error. So we can return a failure, and we can make a string that contains the information about the character we were expecting and the character that we received. So we can use the sprintf function for that. We can say that we expected a character and that we got a different character. We can pass in the expectChar and the C value here. And as you might notice, we're using the result type, which is the success and the failure discriminated union cases, which we had defined in episode number 3. So these come in handy once again because we're going to be using them to indicate whether the parsing was successful or not, and also give information whenever the parser doesn't actually get what it expected. So as this green marker is telling us, we have an incomplete pattern match in this expression, and we need to also deal with a case where there's an empty list. So in this case, we'll just look for the empty list, and we'll just return an error that indicates that we reached the end of string when we were expecting a character. And once again, we'll use the sprintf function for that. We can say that we expected a particular character. We reached the end of input. And then we'll pass in the expectChar. So now we have our most basic parsing function. So let's try this out and see if it gives us the result that we expect. So what we'll do is have a string like take, and then try to pass it through our expectChar function. And since we know that the word take starts with a T, we'll start by expecting the character T. But now we see that the function expectChar is expecting a character list, but we're giving it a string. So what we need to do in this case is make a simple function that takes a string in, then returns a list of characters. And since a string is also a sequence of type character, we can take that sequence and turn it into a list of characters. So let's make a simple function called string to char list, and then it takes a string. Then we'll say list.ofSeq string. And that's it. So now we can go back and pass that, or use that function here on the take string that we have, string to char list. All right, so now we see the normal thing that we expect, which is that the expression doesn't have ignore at the end because this expression is at the top level of the file. So what we actually want to do is send this result value through the printf function so that we can see the output. So we'll go ahead and add that to the end of the pipeline. And we'll use the capital A since it prints out the value in the structured form that the variable is in. So we'll go ahead and select all the code in a file and run it by using Alt-Enter. Okay, and let's run this one little block of code again. Okay, so now we can see that we have a success value, And the success contains a tuple, which has the letter T as a char, and also a list of the remaining characters, the AKE. So that's what we were hoping for. So what happens if we change this T to an R? Let's try to run that again. Now we have a failure that says we expected R, but we got the character T because we have R here as the expected char, and then we have a string take that starts with T. So this is also what we expected. So that's great. Now we have the most basic function we need to start parsing these commands. So what if we want to accept a character that could be either T or R? This is the point where we start to build this idea of combinators, where you can take a simple parser function and combine that with another parser function to achieve more complex behavior. So we'll go and make a new function called parse. And it will take two different parsers. So we'll say parser1 and parser2, and the list of input characters. So with these two parser functions, what we need to do is try to run parser1 and see if it succeeds. And if it doesn't succeed, then we need to run parser2 and return its result. So since we know that parser functions return result values, we can go ahead and just use a match expression directly here. So let's just say match parser1 input chars with success. And since we already have the result, we can just pass that result right through. So let's just say result here, and then just return success result. But if it failed, then no matter what the error message is, we need to go ahead and run parser2 on the input chars. So now we can evaluate this function, and then we can give it a shot here. So let's say parse, and then we will pass in expectChar R and expectChar T. So now we've defined an OR parser, which takes either of these two parsers and then runs them and returns whichever one was successful. So let's go ahead and try that now. So now we can see that since the input string was take, and since we were expecting T, the T actually came through. So if we turn take to rake, and then we run that, we also see that we get a success, and R is returned as the character that was parsed. But if we turn the R to a C, to be cake, then run that, we get a failure saying expected T got C, because expectChar T was the last parser in the OR, so that was the one that had its result returned. So now we have our first parser combinator function that allows us to take two parsers and then put them together to make more complex behavior. One more thing we can do here is define an operator that will allow a developer to use this parse combinator in line in a function. So I'll define that operator and then I'll show you how we use it. So we're going to use the operator definition syntax, which is the parentheses with the symbol inside of it. Then we're just going to assign that to parse. So now that I have this operator, I can take this parse out and then use the operator to define this parser line. And we need to leave these parentheses around so that this gets considered to be one function in the pipeline. So let's see if we can run this now. I'll go ahead and evaluate the operator line. Then I'll run string to careless again, and we'll see that we got the same error because of cake. Change this back to take, run it, and we get this success again. So this makes it a little bit cleaner to define multiple expectChar functions or multiple parser functions and have them OR together. We can also see that you can chain multiple of these parsers together with multiple operators by just adding another operator at the end. And this time we'll say expectChar of C, and then we will make it cake again and run it. And now we'll see that cake is actually accepted. The first letter C is accepted. So as you might notice, parse only takes two parameters, but we're able to chain together multiple OR parse operators to have 3 parsers ORed together. This works because operator definitions are left-associative, and by that it means the operator precedence comes from whatever is leftmost in the expression. So that means that between these two usages of the operator, these two values are applied with the operator first, and then the result of this expression gets applied to this use of the operator. So it just goes left to right. Another way we can use the OR operator is to make a function that can take a list of parsers and then OR them all together. So let's define a function called choice, which is a combinator that will allow this more flexible use of the OR operator. So it will take in a list of parsers, and we'll use the list.reduce function to apply the OR parse function to the list of parsers. So list.reduce will take a list and then successively apply a single function to the items of the list to aggregate them all together into a single final result. So in this case, it will take the first and second parser in the parser list and then apply OR parse to those 2 parsers, and then it will take the result of that OR parse and then apply that to the next item in the list, and then continue to build that result value by applying OR parse to the accumulated result in the next list item. So we can use this choice operator on this line, and then we can turn this into a list. And now we have the choice operator applying these 3 parsers with the OR parse operator. So let's try to run that. Okay, so since the input string was cake and we had these 3 parsers, one of them expecting the letter C, we can see that we get the success here. So what if we change this to a B to make it bake? Run this code and we'll see that we have a failure. So basically the choice combinator allowed us to take this list of parsers and then combine them all together so that one of them can succeed. So there's another interesting thing we can do with this choice operator. We can create a function that can accept a character that is present in an array of characters. So we use an array to define the list of characters that we accept. Then this function will generate all the expectChar calls to parse any of those functions. So now we'll define the anyChar function that takes in a list of valid characters and then pipes it through the list.map function and then applies the expectChar parser to them so that for each valid character an expectChar parser is produced. Then we'll pass that through the choice combinator so that all of these expectChar parsers are ORed together. So now we can change our code here in the pipeline to say anyChar of, and then we can get rid of all these expectChars. So if we go evaluate our anyChar of function and then evaluate our pipeline, we can see what we normally expect, which is expected C got B because we're typing in bake. But we can add B to this list and run it again, and now bake is accepted. And one last interesting thing about this anyChar of method is that we can use F# range operator to say that any letter between A and Z is accepted. And basically what this dot operator is doing is saying that you should generate all the values between A and Z and then create a list out of it. So if we run this code, we can see that bake is accepted, but now we can also see that if we change this to L, lake is also accepted. So now you can start to see how we can build up even more robust parsing behavior out of all these small functions. So now we pretty thoroughly explored the way that you can use the OR parse combinator to combine parsers together and get a successful result if either of those parsers succeeds. But that's not the only thing we need. We also need a way to AND parsers together so that we can say this parser only succeeds if parser 1 and parser 2 both succeed. So let's try to define a new function called andParse. And this function is going to take parser 1 and parser 2 and the list of input characters, and it's going to try to combine those parsers so that both of them must succeed so that the parser succeeds. Now, if we think about the logic for this, we'll need to run parser 1, check its output to see if it was successful, and then run parser 2, and then only return success if parser 2 was also successful. Otherwise, we're going to return failure for everything. So let's start to sketch this out. We'll use a match expression, and then we'll run parser 1 on input chars. And then we'll just go ahead and take care of the failure case. And whatever message gets returned, we're just going to pass it right back out. And then for the success case, we're going to take the character from parser 1 and the remaining characters from parser 1, and then pass them through parser 2. So then we'll do another match expression, which calls parser 2. And then for the input chars for parser 2, we're going to pass the remaining characters from parser 1, then match that with failure. We're going to just pass that right through again. And then for success, we'll take the character from the second parser and the remaining characters from the second parser. And then we'll return success. But now we have a little bit of a dilemma. Because we want to combine parser 1 and parser 2, we need to return the combined output from parser 1 and parser 2. So one thing we can obviously do here is just use a tuple and just say that C1 and C2 are returned as a tuple, and then we also return the remaining characters so that that can be used in future parsers. But now something's changed. Now we don't return the same return type that we had before. Now our success return type, instead of it being a character and the list of remaining characters, now it's a tuple of 2 characters and the list of remaining characters. So this has an impact on how we're able to combine and parse with other parsers in our set of parser combinators. But before we go into how to solve that problem, let's go ahead and try out and parse to see if it works the way that we expect it to. So we'll go ahead and evaluate this code. And now we can go back and use and parse here. And then we can say expectChar L and expectChar A. So that will expect the letters L and A to come in sequence. And since we have the string lake as input, then this should succeed. So let's try to run this. So now we can see that we get a success, and we have the tuple of L and A as a result. But let's see what happens if we change the A to an I to say like. Let's run this. And now it says failure, expected A but got I. So now it actually returned an error for the second character because we've ANDed these 2 parsers together. So since the second parser failed, it returned the error message saying that it expected the letter A, but it actually got the letter I. So that's what we expect. Similarly to what we did with the OR parser, we can define an operator to make it easier to use and parse. So let's do that now. So the operator that we'll use is a commonly used operator in functional parser combinator libraries. It is dot angle bracket dot. And that seems a little bit ridiculous, but you'll see how it composes well whenever we start looking at other operators that are like it. So we'll just assign this directly to and parse. And now we can drop down to this line and just use the operator to AND these 2 parsers together. We can run our operator line and then run our pipeline. And as before, we got the failure, and if we change our I back to an A, we will get our success. So the next obvious step after we have this andParse function is to make a function that can parse an entire string that we expect, so that we can parse this entire lake string and just say expectString lake. So let's go ahead and try to write that function and see what happens. So we'll define the function expectString, which takes an expected string as its input. And much like the anyOf function, we're not going to give in a list of input characters as a parameter because we're basically just composing together functions to return a higher level function that already has input chars as a parameter. So the thing that seems obvious to do here is to take the list of characters in the expected string and then generate the expectChar parsers for those characters and then AND them together. So let's try to do that. So we'll say expected string, and then we will pipe that through the string to char list, since we need that character list. Then we can use list.map and turn that into expectChar parsers. And then we can pass that through the list.reduce function, sort of like how we did with choice, and then use the andParse function to chain those together. So now we have an error marker under andParse. So if we hover over that, we'll see that we have this pretty nasty looking type mismatch error. So what it's saying is that it's expecting a function that takes a character list and returns a result, which is what we expect. And it's looking for a result type that has a character tupled with a character list as the success value and a string for the failure value. And then the same type, the same function type for the other parameters. But instead it was given a function which has a result type of char, a character list, and then we see that at the very end the return type is char tupled with char, then tupled with char list. So this thing has gotten really confusing now. And the reason this has happened is that list.reduce is taking all of the parsers that come from this list.map that comes previously in the pipeline, and it's trying to take the first parser, get its result, and then use that with the second parser. And because the output of expectChar doesn't have the same output type as andParse, which has the char tupled with char, then tupled with char list, then we can't compose these functions because the types just don't match up. So now we've hit the point where we need some additional functions that can help us deal with parser functions that have different return types. And we also need some way to deal with this crazy type string that we keep seeing because it's just a little bit too noisy to really understand what's going on. I mean, it's really difficult to parse what's happening in this list of types. So we can start solving both of those problems by defining a parser type. So let's scroll up here before all the other code and then define that. So our parser type is going to be a single case discriminated union, which is generic, so that we can define a parser type for any type of result that a given parser needs to return. So we'll start it by calling it type parser, and we're going to use the generic syntax to say that A in this case is just any type that can be plugged into this parser type. And then we'll have our single case parser of char list. And this is going to be a function that takes in a char list and returns a result of A tupled with the remaining characters as a char list, or a string, which is the failure message. So now we have a nice type that defines this whole function signature that a parser is supposed to be. And now all of our functions that deal with parsing functions can deal with this type instead of this whole function signature. So we'll go ahead and evaluate this so that it's in our session. And now what you might expect is that F# should be able to recognize this function as a parser and then show all of the type signatures for functions with parser instead of that whole function signature. So let's hover over expectChar and see if that actually happened. Now what you'll see here is that it didn't actually figure out that this is a parser function. You see that it's a curried function with 3 parts that takes the expected character and then returns a function that takes the list of input characters, and then that returns the result for whether the parser succeeded or failed. So the reason why F# type inference can't figure this out is because we've actually defined this as a discriminated union, which means we need to wrap each parser function in this union case so that the type system and the compiler knows for certain that it's a parser. To do that, we have to implement our own currying of our parser functions so that we can do this wrapping of the function with the parser case. So let's try to do that real quick with the expectChar function. So we'll drop this into a new line, and we'll say let inner parser, and then we will indent all of this code. So now we have a nested function called inner parser, which then takes a list of input characters. And now we can say parser inner parser. So what this does is takes this nested function definition and then returns it wrapped in the single case discriminated union called parser. Now if we hover over expectChar, we'll see that it takes in an expected character and then it returns a parser that returns a character. So now any place that we've used expectChar in our code, it's going to have to become aware of the fact that we've wrapped this parser function inside of our discriminated union. So if we scroll down, we can see the first error from this. If we hover over choice, it says that we're expecting a function that takes in a list of parsers and then returns something. But it's actually been given a list that returns an input and returns a result, a list of those signatures, and then returns some other stuff. So we need to make some changes to our code so that all of our existing functions now become parser aware. And before we do that, probably it's a good thing to just go ahead and double check the expectChar function to make sure that it still works. So we're going to evaluate this. And we'll scroll back down to our test functions. And we'll just go back to the plain old expectChar of L. So we have an error here. And it says that it's expecting a function that takes in a character list and returns some value, but instead has the type parser of char. So this is indicating to us that the pipeline now has this value that's returned from expectChar of L, and it doesn't know what to do with it because it's not a function anymore. It can't actually pass it through the pipeline because it can't execute it. So what we need is a way to execute parsers that were defined in this way. So let's go back up to this definition and create a new function called runParser. And then we'll take in a parser, and then we'll take in the list of input characters. And we're going to use parameter destructuring here to extract the parser function from the parser discriminated union. So we'll say let parser func equals parser. So it takes this parser discriminated union and then uses this syntax to say, okay, I know this is supposed to be a parser, which is a single case discriminated union, and I know that it's supposed to contain this function with this particular signature, so give me that function that's contained within and bind it to this name parser func. So now we can just run that parser function with the input characters. And if we check the signature of this function, it takes in a parser and a list of input characters and then returns the result. And this function is properly generic in that it has the apostrophe A saying that for any generic parser of type A, we're going to take in a list of characters and then return a result that has that generic type of A as the output. So we can go ahead and run this function. And now let's go back and we'll use runParser here. To apply this parser of expectChar to the input. So if we run this, we'll see that we're back to the expected output of success with L being the first character and then A, K, E as the remaining characters. So now we have our basis for converting the rest of our code to use this parser type. So anywhere that we've been taking a parser function and running it in the past, we need to go back and then wrap it with this runParser function. So let's go back up to our parse function, where we've been taking these parser1 and parser2 functions, and then just pass those things into runParser. We'll do the same thing for the failure case. So now you can check the signature of parse and see that it takes parser1, which is a parser of A, parser2, which is a parser of A, which makes sense because we're ORing two things that return the same type. And then it returns a result where the generic type A is the result value. So now we'll see here in the choice function that parse has an error. And it says that type parser of A does not match the type and gives us a signature that looks pretty similar to what we expect from a parser. So why is it that it can't tell that this parser A is the same thing as this char list that returns this function that takes a char list and returns a result? Well, the reason for this is that I forgot a very important step in the parse method. It's not enough to just call runParser on the parsers. We actually have to convert this method into the same pattern that we used in the expectChar function. So that means we need to define an inner parser function. And return that function wrapped in a parser type. And also don't forget to put the equal sign at the end of the function declaration. So now you'll see that parse actually returns a parser as its output, and that's the actual expected output. And now you can see that choice also has become aware of that. And now choice takes a list of parsers and then returns a parser. So let's go ahead and reevaluate these functions so they're ready. Okay. So now anyChar also is aware of the parser type because that has flowed through there. So we'll go ahead and reevaluate that as well. And now we take a look at parse, and parse has one of those ugly signatures. So let's go ahead and try to fix this function. So we'll drop down, we'll make our let inner parser to define our nested function. Then we'll return that inner parser wrapped in a parser type. So now we also need to call runParser in front of the parsers so that those will run correctly. And now if we check the parse function, we'll see that it takes in parser1, which is a parser of type A, and takes in parser2, which is a parser of type B. Then it returns a parser type of A tupled with B. So now this becomes way easier to understand. It's really clear now that the parse function takes two parsers, runs them, and then it tuples their results together and returns that as a parser type. And it's a parser type result because this is a combinator. We're defining a function that takes in two parsers and then returns a new parser function that combines their results together. So this is actually what we expect. So now let's go back to our expectString function that we tried to write and see what the error is here for parse. So it says that in this list.reduce call, it expects a function that takes two parsers which return characters, and that function should return a parser that returns a character. But in this case, we are giving it the function parse that returns a parser that returns two characters tupled together. And this is because list.reduce has a signature which it looks for a function that has three parameters that are all the same type, or two parameters of the same type that return the same type. So because we want to take two parsers, or actually a list of parsers that return characters, and then we want to turn those into a list of characters that are returned, this list.reduce function is not going to work for us. So what we need now is a function that can take a list of parsers, run them all, and if they're all successful, take all of their result values and then put them together in a single list and then return that as a parser function. So we'll create a function that can run a list of parsers in sequence and then aggregate all the results. Sort of like the list.reduce method, but more aware of parsers. So we'll create a new function called sequenceParsers and take in a list of parsers. And since we need to loop over this list of parsers, theoretically we could just use one of the list.map functions, etc. But I thought this might be a good opportunity to show how to define a recursive function in F#. So to do that, it's actually really simple. All you need to do is just put the REC keyword in front of the function name. And now this has been defined as a recursive function. And the thing about recursive functions that are interesting is that, yes, they can call themselves, but if you design your function properly, then you can make use of a property called tail recursion, which basically removes the penalty of calling a function recursively if it's going to call really deep into the call stack. So if you've ever used recursive functions before in a language that doesn't have proper tail recursion, then you might have at some point hit a Stack Overflow exception, which basically means that you've done so many function calls that it basically has terminated the application because you've run out of room for function calls. In the case of tail recursion, the compiler actually converts the recursive function calls into something more like a loop. So you can make as many calls of that recursive function as you want, and it doesn't hit the process's limit for function calls. So writing a recursive function like this allows you to have a simpler function definition that has recursive behavior, but doesn't have any penalty as far as function call stack limitations are concerned. So in this case, sequenceParsers will take this parser list and decompose it into the first parser and the list of the rest of the parsers. Then it will try to execute that first parser, get its result, and then recursively call itself on the remaining parsers, and then combine the results that came from those remaining parsers with the result from the first parser of the list. And I know that was a mouthful, so I'm going to write the code now so that you can see what I was talking about. So we're going to use a match expression to match parser list with parser and remaining parsers. And once again, we have this : syntax, which is the decomposition operator for a list to take the first item off the list and return a list of the remaining items from that list. So now what we want to do is return a new parser, which combines the first parser with the parser that's generated from the remaining parsers, which performs the aggregation of all their results. So we can say parser : and this actually will join those items back together. We'll put the parser back on the head of the list. And then we will say sequenceParsers with the remaining parsers. And this is a place where the recursive call comes in, because we're taking the remaining parsers, which is the list after taking the first parser off. Now we're calling this function recursively on the remaining list. Oh, and it appears that I forgot the S. Okay, and we also need to deal with the empty list case. But actually, I'm going to go ahead and add the empty list case above, just to make it clear where the tail recursive part of this function is. Generally, with a tail recursive function, the very last thing that happens in the function must be the recursive call. And this is how the compiler is able to know that it's a tail recursive function and then convert those calls into something more like a loop. So in the case of an empty list, we're just going to return an empty list. So now let's check the signature of our sequenceParsers function to see if it is actually a parser. So when we hover over that, we see that sequenceParsers takes a parser list of type generic A list and returns a generic A list. And this is not correct. What we'd expect to see here is a parser list, which is a list of parsers of generic type A, which returns a parser of generic type A list. So because we know that's what we expect, let's go ahead and just fill in the blanks here so that F#'s type system can help us fix the rest of this function. So parser list, like we said, is supposed to be a list of parsers of generic type A. And the function is supposed to return a parser of A list. And at this point, we can see that we've got some definite errors here. And we're not going to go over these in detail right now because we actually have quite a bit more work to do before we can fix these problems. And I would like to try to work backwards from this point and try to give you everything you need, but it actually ends up being fairly complex to work backwards from here. So what I'll do is start to add the functions we need and build them up so that we can finally get back to finishing our sequenceParsers function. So one common thing that you'll see in functional programming languages is when you're dealing with combinators or just function composition in general, you're going to have functions that take some action on other functions. So you're basically building layers of abstractions with functions that take functions and perform some operation on those functions. This is where functional programming can start to become a little brain melty. So I'm going to try to explain this as well as I can and try to show you how all of these different functions that we're going to write actually fit into the bigger picture. So one of the most fundamental functions that we're going to need, which can operate on our parser functions, is a function that can take a parser, run it, and then execute some function that manipulates its return value. So for that, we're going to write a function called map_parser. And that's going to take a map function and also a parser to apply that to. And you can think of this like the map function that's common in functional programming languages, where you have some value and then a function that takes that value and then turns it into another value, a basic map operation. And then the map function will run that function that's provided on the value and then get the value back. So this is one of the common tools for dealing with higher order functions in functional programming languages. So since this map_parser function also is supposed to be a parser, we're going to use the same pattern for defining it as a parser. So we're going to say let inner parser with inputChars, and we're going to do a match expression, which then runs that parser on inputChars. And if there's a failure with a message, we're just going to pass that through. And if there's a success, we're going to use this map func and return a new success with the map func converting that result. And now we'll just go wrap this back in the parser type. So if you look at the signature for this, we're taking in a function that converts some generic type A to generic type B, and then we're returning a parser which converts parser of generic type A to parser of generic type B. So this will allow us to convert the result type of some parser, and that ends up being a really useful operation that we can use to build other higher order functions in our combinator library. So I'll go ahead and evaluate that before moving forward. And the next thing that's useful to have is a function called apply. And this is a way to wrap a normal function inside of a parser so that it can be used as a parser, but actually it doesn't parse anything. All it does is apply a function to another parser, or the result of another parser. So it might sound a lot like the map_parser function that we just wrote, but actually it's a use case of the map_parser function. So we can write let apply parser, and then we can say our function to use as a parser and our parameter that is wrapped in a parser. And now we're going to run these two parsers, the func as parser and the param as parser, and we're going to AND these together so that the results of these two parsers are tupled together. Then we're going to take that tupled output and run it through the map_parser function. And the map function we're going to use for map parser is an anonymous function, or a lambda function, which will decompose that tupling of the results of these two parsers. Since we know this one is supposed to be a function result, we'd say f, and this one is supposed to be the parameter, we'll say x. So we decompose that tuple, then we take the function and run it on the parameter. And now you can see that apply parser takes in a parser which returns as a result a function that converts A to B, and also a parser that returns some value and then returns a parser function that returns a value of type B. So it's basically using this function that comes from this func-s parser to map the value that comes from param-s parser from generic type A to generic type B. And this apply parser function is something that's worth having an operator defined for it. So we'll go ahead and define an operator and then just pass that through to apply parser. And also, since we have this apply parser function, we have a function as a parser, we have a parameter as a parser. Sometimes it might be good to have a parser function that can basically just return a value wrapped as a parser. If we need to pass a parameter into a function that we're using from a parser, we're going to need to be able to wrap that value in a parser type so that it's accessible in this world where we're dealing with everything as parser functions. So we can define a function called return as parser, and then we will say pass in the result. And we'll use the typical parser function model here. And since all we really want to do is take this result and wrap it as into a parser result value, we're going to always return a success. And we're going to pass that result. And we're also going to pass the input characters, because this parser function that just returns a value doesn't consume any of the input characters. So it just exists purely for the purpose of returning this success result with the value that we want to be the result for this parser. And we'll finish this function off by wrapping the inner parser func as in the parser type. Okay, we're almost there. We have one more function that we need. So what we need now is a way to take a normal function that takes some input and some output that's not a parser, that doesn't deal with parsers at all, and then turn that into a parser function. Because we need to be able to use that in our apply parser function when we want to apply some normal function, but in the scheme of our parser abstraction. So in functional programming, this operation is generally called a lift. So we're going to make a lift function. So what we need is a function that can lift a function to a parser, and this function we will assume accepts two parameters. So that's why we're going to say lift to parser 2, because this is a lift function for any function that accepts two parameters as input. And this will take the function to lift and the two parameters. But since we're living in parser world now, we can't just give it two normal parameters. We actually have to give it parameters that are wrapped in the parser type. So we'll call those param as parser 1 and param as parser 2. And since we need to lift this function into the parser world, we're going to use our return as parser function to wrap that function in a parser value. So we'll say return as parser func to lift. And now we can use the apply parser function to apply the function that's wrapped inside of this parser value, which comes from calling return as parser on func to lift, onto some parameter which is also wrapped in a parser. So in this case, we can use the operator we defined for apply parser and apply that to param as parser 1. So what this has done is it is taken the parameter value that we have from calling return as parser on func to lift and then applied it to param as parser 1. But since func to lift actually takes two parameters, we need to apply this to the second parameter as well. So at this point, this is a partial application of func to lift wrapped inside of parsers, basically. So we can just run that through the second call of apply parser and run that through param as parser2. So now if we look at the signature for this function, we can see that func_to_lift is a normal function that takes parameters a or of generic type A and B and returns a value of generic type C. Then it takes in a parameter as a parser, the first parameter, which is a parser of generic type A, and also takes in a second parser of generic type B as a second parameter. Then that function returns a parser of generic type C. So it basically just takes this func_to_lift, applies it to the parameters that are wrapped in parsers, and then returns a new parser function that has the output of that function wrapped as a parser. Is your brain exploding yet? Okay, now we can take everything we've built here and then apply this to the sequenceParser function so that we can start going back toward parsing strings. So now in our sequenceParsers function, we need to have some way to take our parser and then our list of remaining parsers and then join them together in parser world, not just in normal function space. We need to lift this up into parser land so that it can then be combined with other parser functions. So the typical function that you would use in functional programming languages to join an item with the remaining items in a list is something called cons. And this is something that if you've ever used Lisp before, you've seen this. So we'll let cons head rest, which is the head of the list, and then the rest of the items of the list. And then we'll use the F# operator for joining the head with the remaining items in a list to combine those two. So now cons takes a item of generic type B and a list of generic type B, and then returns a new list of generic type B. So basically just puts that first item onto that list. So now we can use our lift function that we created to lift this cons function into the parser space. So let's say let cons as parser equals lift to parser2 cons. So now this function that we've defined will take in a parser of some object type and a parser of some object list, and then return a parser with an object list as its result. And now that we have this cons function, we can go back here and take this cons out that we had done manually before, and then run this through cons as parser. And then we will put this inside parentheses so that it's obvious that these are for one function call. And lastly, we have this list that is not of type parser of a list. So we need to wrap this in a call to return as parser. So after all that work, let's check out the signature of this function to see if it's right. We can see that parser list is of type parser a list, and the function returns a parser of a list, just as we have specified here. So now we can just go ahead and get rid of the typing because we've made the function have the right signature that we were looking for. And now we can see that the function's signature is still the same, parser a of list, and then parser a list. Okay, so let's go back to expectString. And now what we can do is, since we have this list of expectChar calls, we can just turn this directly into, or pipe this directly through the sequenceParsers function. And if we check out the signature of expectString, we can see that it takes in a sequence of type char, which is basically a string, and then it returns a parser that can return a character list. But we don't want a character list as a return type. We actually want a string because we're trying to parse a string. So now we can use the fancy map_parser function that we had made earlier to take that character list and turn it into a string. So we can call map_parser. Now we need a function that can take a character list and turn it into a string. So let's quickly define one of those. Let char list as string chars. And then we'll create a new system.string instance. And then we're going to turn the list of characters into an array. And now this should have us with a function that takes in a character list and returns a system.string. So now we'll pass that function, character list is string, into map parser. And now we'll check our signature for expectString, and our result is a parser that has a result of type system.string. So after all that work, we finally have a function that can, based on an expected string, parse that string, and if it was successful, it should return that string. So now we're gonna have to go ahead and run all this code since we haven't been evaluating these functions. Okay. So now we have expectString that's been evaluated. Theoretically, it should work. So now we can change this to expectString and say lake. And hopefully this will give us the result we expect. Great. So now we see that we have success and we have a string lake returned. So we can actually change this to Luke and run it. And we have the failure that we expected. Expected A got U because we're passing in Luke and we're expecting lake. So that is working correctly. And now to prove that we've done this in a way that can be composed with other parsers, we will OR this expectString with another expectString of take, and then run that with take, and now we see that take is successful. So now we have built another layer of abstraction where, based on an input list of characters, we can expect a particular string, and if that string is found, we get that string back. So since this was a pretty complex series of steps, I'm going to go ahead and end the coding part of this episode here, and then we can pick up on it on the next episode where we're going to expand on what we built here to finish out our command parser and also see how we can leverage F#'s computation expressions to make this code even simpler. So that concludes our introduction to writing parser combinators using F#. In the next episode, we're going to continue our work on our parser library so that we can parse the actual commands for the game, and then also try to use F#'s computation expressions to simplify our parsing code and logic so that it becomes way easier to write. So if you enjoyed this episode and you're not yet a subscriber to this channel, don't forget to click the red subscribe button below so that you get notified for future episode releases. So that's all for this episode of the Dev Aspect. Thanks a lot for watching. We'll see you next time.